Okay, folks, this is the play pause it on free fall. So please write that down. That is the title of the lecture. And the first, you don't have to write this down, but I've learned that calling this free fall is a bad term because when I put a question on the test and somebody is both jumping up, like they jump up and then they jump down, people think that only the down part is free fall, which makes complete sense because you're only falling on the way down and you're ascending on the way up. However, I think the reason it's called free fall is that the object is free from all of the other forces except for the force of gravity. So that means no jetpacks, no air resistance, no trampolines, sad face. So when this person is touching the trampoline, they're not in free fall. Their acceleration is not negative 9.8, but when they are doing any kind of stunts, whenever they're not touching the trampoline, whether they're on the way up or on the way down, they are still in free fall. All right, and a famous dude named Galileo dropped a big rock and an even bigger rock and showed that they both fell at the same rate. The acceleration of both of those rocks was negative 9.8 meters per second. Negative because the Earth is pulling them down, even though they're clearly speeding up. The trick is, as you'll see in the second play pause it, the trick is you just need to get rid of air resistance. And so this guy's going to drop a bowling ball and a feather in a vacuum. And clearly, without the vacuum, the feather is, because it has so little inertia, is affected by the air molecules, slowing it down. But that's because it's really not in free fall because of air resistance. Okay, so you're gonna see that in a separate play pause it. You will be given this constant, but by the end of this unit, you will probably have it memorized. The acceleration due to gravity on Earth is negative 9.8 meters per second squared. That is also called G. But be really careful with your minus signs. And if what I say in the next minute is confusing, just reach out as you're doing the problems. Your position function, and notice I switched from X to Y because the motion is up and down. If you're like, that's too many new variables, I'm totally fine if you call it X at this point. So your position function is your initial location plus your initial velocity times time plus the acceleration due to gravity. But we know that the Earth is pulling down, so we know that's minus. We don't want G itself to be negative 9.8 because then you'd say plus GT squared over 2, right? And the minus would be hidden inside the G, and it would look like a concave up parabola. And you know that's not true. You want the minus sign out front so that your brain can see, oh, this is negative. So basically what I'm trying to say is G itself is 9.8 and the acceleration due to gravity is negative G. Okay, so small technicality, but I don't want you to have double negatives floating around. So as you do the problems, just pay attention to the minus sign and let me know if it's not working for you. Okay. Oh shoot, this is not working as an animation because it's in Cami, but please write this down. You've got your position versus time graph for something that was thrown up in the air, reached a maximum height of 150 meters-ish, and then came back down. What is true when the object lands is that it has no altitude. We know where it is. It's on the ground. So what is true when it lands is that y is 0. So I'm just going to pause and ask you, what do you think people say is true when it lands that is wrong? Okay, what I often see people do that I'm trying to prevent you from doing is they say that the speed is 0 because what happens after something lands, the volleyball hits the ground and it's just sitting there chilling at rest, and so its V is clearly 0 for a long time. So your brain associates being on the ground with v equals 0. Okay, that is not true. If that were true, that it hit the ground with a speed of 0, then my joke is I could take you all skydiving, we could jump out of the airplane and gain a lot of speed and then say, oh, but we're going to be safe. We don't need a parachute because when we hit the ground, v is 0. Okay, clearly that's not true. What is true when it hits the ground, and you will use this in the baseball lab, is that it has no altitude. The position is 0, not the speed. And you can just see this kid having fun, jumping into puddles. If they hit the ground with no speed, they would not make a splash. Okay, so that's the common misconception. Please don't fall into that trap. And then the last thing we're going to do, remind me if you want to do this in person. We can have somebody try to catch ooh, look at this, a $20 bill. What you are going to do is calculate the time. So please get out your calculator. It takes the bill to fall 0.16 meters. So the length of the dollar bill is almost perfectly 0.16 meters. We care about this point in the dollar bill. So I'm going to call the person's fingers the origin. That's our reference point. This is where, and we care about this last little part of the dollar bill because that's the last millisecond we can catch it. So the initial height of the dollar bill is 0.16. That's x naught. And it's going to fall until that point of the dollar bill is at x equals 0. We are dropping it from rest, and we're dropping it on Earth. So the acceleration due to gravity is negative 9.8. So choose which of the following position functions is the correct one. Then I will confirm that you have the right position function, and then you're going to solve that for time, and then we're going to be done.